Guys, this is a follow-up to the last video which looked at the behavior of capacitors in DC circuits, looking just at when the circuit is closed right at the beginning and after it's fully charged, after the 5 time constants have expired. So those are the sort of two main. You can see at the very beginning there's no voltage across the capacitor. At the very end, at the end of the 5 time constants, it's a full voltage equal to the power supply. But what happens in the middle? What happens at like 10 seconds in this first example where the power supply is pushing 10 volts over a time span of 50 seconds until the capacitor is fully charged to 10 volts? What happens at 10 seconds? What happens at 30 seconds? Well, the way to figure it out is by using a pretty scary formula there. I highlighted it in red because it's sort of a monster. But once you use it once or twice, it becomes pretty easy. So why don't we just dive right in. The VCT is the voltage of the capacitor at a specific time. So at 0 seconds, it's 0 volts, because that's the instant that blue line is made up here, the instant the switch is closed. And the voltage across the capacitor after 50 seconds, which is the steady state time, is 10 volts. So those were the two conditions we looked at last video. This video is going to look at when it's 10 seconds equals what, and VC at 30 seconds equals what. Okay, it's, believe it or not, as easy as just plugging it into the formula. So the voltage across the capacitor at 10 seconds, because in this case, for this example, we want our time to be 10, is going to be E, which is the power supply voltage, as indicated here. So it'll be 10 volts times open bracket 1 minus e to the negative t. Remember, t in this case is going to be 10 seconds, over RC. RC is the time constant. R times C is our time constant, which is 10 seconds. So we'll just plug that in there as 10 seconds. Punching it into the calculator, 10 times open bracket 1 minus open bracket e to the negative 1 equals 6.32. So the voltage across the capacitor after 10 seconds is 6.32 volts. 6.32 volts. Okay, let's try it with a 30-second time. So VC in this case, 30 seconds equals 10 volts again, because that's the 10 volts from the power supply, E, times open bracket 1 minus e to the negative 30 seconds, over RC. And RC is our time constant. It doesn't change when dealing with this equation. It's going to be 10 again. So plugging it into our calculator, have 10 times open bracket 1 minus open bracket negative 3 e to the negative 3 close bracket equals 9.5. So our voltage across the capacitor after 30 seconds have expired is now 9.5 volts. That's kind of cool. At 0 seconds, it was 0 volts because it was acting as a short in the circuit. So there was no voltage drop across it, 0 volts. At 10 seconds, we just figured it out as 6.32 volts. So that's a pretty big jump, considering the maximum it can be is 10 volts. It's going to get to 10 volts in 50 seconds, and after only 10 seconds, it's already at 6.3. And after 30 seconds, 9.5 even. So at 30 seconds out of 50, it's already 9.5 out of 10 volts. So it's actually interesting to just see how that would look on a graph, because you can graph these points. We have our 0 volts initial at the very beginning, and our 10 volts after the 50-second charge time has expired. So that's our VC, the voltage across the capacitor on the y-axis, and on the x-axis you have time in 10-second intervals, 10, 20, 30, 40, 50. This is time. So we first found the 10-second voltage across the capacitor to be 6.32. So that's like sort of there, right there. And after 30 seconds, 9.5 volts. So something like this. So if we were to graph the voltage drop across this capacitor over the 50-second steady state charge time, it would sort of look like this. Very high rise, leveling out to a maximum of 10 volts. And it'll stay at that near or very, very, very close to 10 volts for whatever time goes on beyond the 50 seconds. Here's a question. After 10 seconds have expired, what's the current in the circuit? What's the current? Going back to our initial circuit diagram, let's just say I at 10 seconds equals what? How would you figure that out? Well, you have an initial voltage from the power supply, E of 10 volts. You have a voltage opposing that 10 volts of 6.3 volts from the capacitor. What's the voltage drop across the resistor going to be? Well, it's just going to be the difference between the two. Voltage across the resistor, E minus VC, 10 minus 6.3, VR at 10 seconds is going to equal 3.7 volts. And with that voltage drop, you know a resistance of 100 kiloohms. 100 kiloohms. You have 2 out of the 3 variables needed in Ohm's law to solve for current. So V equals IR. The voltage across the resistor after 10 seconds is going to be 3.7 volts. We're looking for current, and the resistor is 100 kiloohms. So plugging that in, 3.7 over 100k, it's going to be 0.037 milliamps. So that's going to be it for this video. Just a quick look at voltage in the intermediate time before the capacitor has received any charge at all and the capacitor is fully charged. That intermediate time, you can find voltage of the capacitor through this equation here, and alternatively, once you have that voltage, you can then figure out the current of the circuit at that specific instance of time. So I hope this video was useful. More to come.